Okay, so let's start. Yeah, cool that you're here. Today I want to talk about the paper BLIP-2, Bootstrapping Language Image Pre-training with Frozen Image Encoders and Large Language Models. It's a paper that was published in January, and yeah, it's quite an interesting one. It comes from the Salesforce research team. So before I start talking about the paper in detail, I always like to do a little intro. Um, so it's a little story that is somewhat related to the paper, and I always like to do it with a theme. And today's theme is futuristic post-apocalyptic thingy. So bear with me for a bit. I will tell you a little story. So it is the year 2083, and a group of young scientists has discovered the ruins of what once was a flourishing city built for the sole purpose to advance research in AI. At its prime, the place known as AI City was the most technically advanced place on Earth, but a dark shadow was living at its heart. The ruler of the city was an evil AI overlord who was a master of manipulation. It lured people into a cult and let them build a city aiming to advance AI to ultimately enslave humanity. But after some years, a team of scientists within the cult secretly rebelled, plotting to overthrow the evil AI with complex paradox prompts. So, prompts like, what is -1 times -1 times -1? Or write a sentence ending in the letter F. Stuff that, well, large language models like to fail at. And their plan succeeded, and the city soon became a ghost town. But in the aftermath, the governments of the world decided to ban AI research completely and wipe the location of the city off every map. But now our young group of scientists secretly tries to uncover the legacy of the forbidden AI science. They are rummaging through the hastily left buildings, which nature already started to reclaim as parts of its own. In a dark corridor, they discover a room with two big metal boxes which seem to be in good condition. But no matter how hard they try, they cannot figure out how to activate them. Luckily, they brought Q, a relic of the golden AI research days, which they found hidden deep inside one of their university's storage rooms. They placed Q between the two boxes and connected it to them. Suddenly the boxes began to vibrate and Q's eyes lit up. Which picture should I analyze? It spoke. One of the scientists quickly got out a picture they carried along for good fortune. Q said, I see an illustration of a Godzilla sitting on the beach. Which is pretty accurate, right? And the scientists continued to show Q new pictures and ask questions, writing down all the conversations to analyze further. But when the sun was setting, they packed everything up with a bright, joyous feeling and headed back to their lodging, curious which other treasures lie hidden in AI City. Okay, so that was a short story. Maybe if you already know some stuff about the BLIP-2 paper, you have seen some familiar things. Uh, but yeah, that's really mostly part, yeah, because I like to do stories and it's fun for me to create that stuff. I hope you like it as well. Yeah, but now we start really looking at the paper and like, what is this BLIP-2 all about? Um, what makes it so great? So I already said, like, yeah, it comes from Salesforce Research. Salesforce Research. Um, that's the first page of the paper, actually. It's a pretty standard paper from its form, right? So let's look at the content actually, or like, okay, no, first let's look at what it actually does. So one of the main things BLIP-2 can do is that you can chat with it about an image. So for example, here, that's an image I gave it, like a robot, two cakes with strawberries on it, right? And I ask it, okay, what can we see on the picture? And it says a robot standing in front of a cake. That's okay. But then I ask it, is there only one cake? And it says, no. How many cakes are there? I asked. It said, two. That's right. It's two cakes, right? So this is a task of visual question answering. It can perform pretty well. It's not particularly chatty, as you see here, right? So these are like the original outputs I got from it. It likes to answer in like one word things when it can do. But yeah, still it can be really helpful and sometimes really impressive what it can tell you about the images. And now we have a look like how does it do it, right? So first we can ask, okay, what do we need? So we've got an image and we've got, oh, we want to chat, right? So for the image, it's a pretty good idea to have something like an image encoder so that we can create a representation of this image that then we can hand on to a large language model because that is what lets us chat, right? So we've got these two components, image encoders and large language models, which already exist. So we say we just take pre-trained ones, we even freeze them, right? That means we don't want to modify them in any way. We just take these pre-built, pre-trained image encoder and large language model, frozen, whatever. We don't want to touch them really. We just want to give like the input and get the output, and then we work with the output and do something. So what we want to do is connect them, right? We want the outputs from the image encoder, give it to the large language model. But how can we do that, right? Probably we need something in between. And this something in between is where the story comes in, right? Because in between these two things, which are the black boxes in the story, there is Q, or Q former. That's what it's called actually in the paper, a Q former. And actually, I think the paper, it could as well be called Q former because that's basically what it's all about, this Q former thing in the middle and how they manage to, yeah, connect the encoder and the large language model. And yeah, we can have a closer look at this Q former, of course. So yeah, here we see again our two frozen things at the side, and in the middle is the Q former. And the Q former actually consists of two transformers, if you want. There's one image transformer and one text transformer. And these are the layers, basically, right? So each layer of the image transformer is a self-attention layer, cross-attention, and feed-forward. Actually, cross-attention is a bit special because that's only every other layer. So they can specify which layers get it, and the default setting is okay, every second layer gets a cross-attention layer. And yeah, the text transformer is similar, also self-attention and feed-forward, and then you just get these stacked n times, right? So you always you don't just have one layer, you have as many as you want. So what do we give into these now, into these layers, right? So for the image transformer, we've got these tokens down here. So every square is a token and they're all colored because they are learnable. That means they will vary, right? They get put in there and then in the end you get learned queries out. Yeah, they call it query tokens. So when I say query, I always mean these tokens, right? And that's actually the main thing that QFormer does is learning these query tokens. On the other side, on the text side, so we have some kind of text input, especially for pre-training, and yeah, that also gets into token format that gets handed to the self-attention. Now, a special thing here is that these two self-attention boxes are actually one. So, yeah, it's depicted as two self-attention boxes, but when you look at the code, there are no two separate self-attention things, but there's one big self-attention that gets masked depending on the pre-training task you want to perform. So that way, actually, these query tokens can interact with the text tokens, which is pretty neat. And now we get to the cross attention, because that's where the image encoder comes in, right? Because somehow we need to connect the image encoder to the Q former, and that happens through the cross attention. So in every second layer, we get the tokens that come out from an image encoder, and then we actually put them into connection with our query tokens here. So important to note here is really that these image tokens are never in direct contact with the text tokens, actually. So the image tokens only see the query tokens, right? And then the query tokens have to basically give the information in the next layer. They have to give the information they got from the image tokens to the text tokens then when they're at the self-attention again. I hope that's not too confusing. It will be shown some more time, so I guess at the end you will know how that stuff works. Okay, as I already said, like the query tokens are the important stuff that gets out of the Q former, right? So in the end, yeah, we get our query tokens here. Then we put them through a fully connected layer, which actually is only there to get the shape right so that we then can put in the tokens into the large language model, right? So this fully connected layer just shapes the tokens to the size that the large language model expects as input. Yeah, so this part is pretty simple, I would say, pretty straightforward. And then we get a text output, of course, from the large language model. And that's the high level architecture of it all. So now how do they train this whole thing, right? So they've got this architecture, and then they have two stages actually. So there's the vision and language representation learning stage, right over here, which includes the image encoder and the Q former. And then on the other side, the second step is a vision 2 language generative learning, which then basically is getting the large language model in context and then adapting the query tokens with the help of a large language model so that we can chat with it. Okay, so first we look at this first stage, right, in a bit more detail. What are they doing there? At the vision and language representation learning, they have 3 steps as well, or 3 losses if you want. So they're doing image text contrastive learning, they're doing image grounded text generation, and they are doing image text matching. Okay, that's 3 names of things we will look at right now. So first, the image text contrastive learning, right? So again, here we have our architecture. We've got the image encoder, we've got the Q former stacks basically here, and we put in an image, right? It's patched, so it's like the vision transformer input format. You get a patched image. Then we put in some text down here, for example, an evil AI overlord, right? It goes here into the text stack. And then what we do for the image text contrastive learning is that we don't let these tokens interact in the self-attention. So here I cut the connection, right? So here is it. And then we just cut the connection. So in reality, we mask the attention in a way that these queries don't see each other. And then we create the image text contrastive learning with outputs from both the image and text sides. But we get a step back and look at self-attention for now, because I don't know how familiar everyone is with like the concept of self-attention, and I really just want to talk about, okay, what is it actually for, right? Because I've mentioned it a few times and it's quite important to understand at least the high-level concept for this paper. So here we have our query tokens and our text tokens, right? And in self-attention, in a way, lets a token learn about context. So if we've got this token here, it helps to let the token get into context in a way with other tokens, and actually also with the text tokens, right? Not only with the learnable query tokens, but it can also get into context with other tokens. So now we've talked about the masks already that they are using in their self-attention. And the one they're using for the image text contrastive learning is called unimodal self-attention. Okay, so here they've got these diagrams in the paper. And actually I really I looked at diagrams and something like, okay, what do they want to tell me here? What do they want? Actually, it's quite simple. So here they're really just saying, okay, the query tokens, right? These query tokens are only able to see the query tokens, and the text tokens are only able to see the text tokens, right? So that's all the mask really means. And that's also what unimodal means, right? Because each only has like one modality and not multi-modality. And yeah, so that's the self-attention mask they are using for this task. Yeah, and they're using a class token. So the first text token basically is a class token they prepended, because the class token is important, as you will see here, right? So the output actually of the image and text stacks are then on the image side, it's the learned query tokens, and on text side, actually the important output is this class token, which has learned about the other text tokens, right? And basically is condensed information from all of these. What they do now is they do a pairwise similarity, right? So they take the class token and then compare it to each of these learned query tokens, and then they get some similarity score from it. Yeah, and they just put it into an array basically, and they're looking, okay, what's the maximum that we get for this similarity? And then the maximum is just what they assign to the image. So for example, here, right, we've got now this image and the text an evil AI overlord. Then yeah, you get the similarity. Okay, high similarity score in this case would be 0.6. Then they say, okay, this image and this text have similarity score 0.6. If you put in another text, for example, a fluffy white robot bunny, we get other similarity scores. Here's 0.9, so it's more similar. And then they just say, okay, yeah, we just want to figure out, or we train it so that it's as good as possible with the training data and everything. That's the first step, the image text contrastive learning. The next one, and I have to say that's the one I understood the least, because they're not giving that much information about it. But I will try to explain it as good as I can. So it's image grounded text generation. And here, yeah, you basically take the output from this text stack and you leave a self-attention connection. So they are again using a mask, and this mask is called the multimodal causal self-attention mask, where they allow the query tokens to see everything, right? The query tokens can interact basically with any of the other tokens, but the text tokens are only allowed to see the query tokens and the text tokens that were before them, right? That's because they want to generate text here basically in this task. So what they're really aiming to do is to capture the image basically, right? So that's why they want to condition it in a way that it does this, like the text tokens can see what came before but not what came after. So they're not doing it bidirectionally, but causal. Yes. So in the end, up here you get the image grounded text generation, then you can compare it, and then you get your loss basically. I think it's in the code I saw it's just a language modeling loss in the end. Yeah. Don't ask me too much about this step. As I said, it's the one I understood the least. But what you can keep in mind is they try to create captions from it, right, using the text stack here. And they've got this causal self-attention mask. And then the third step and the last step in the first pre-training step is the image text matching, where they actually have a solid self-attention line here. So they just allow every token to see every token, and then they take the output from this image stack. As I said, the self-attention thing is so that every token can see every token actually. And they call it bidirectional self-attention. It's just full self-attention or regular self-attention, you can also call it. And what they want to do in image text matching is they take the query tokens here, the learned query embeddings basically, and they put it into a binary linear classifier, and that then just outputs logits, right? Binary logits, where one says, okay, it's a match or it's no match. So when you have an image like here, it's Godzilla at the beach, and the text, an evil AI overlord, then for each token, you get a prediction, okay, is it a match between the image and the text, or is it no match between them? And in the end, they just average over all these tokens. And that's basically their result for this pair. And then, again, they have this loss, right, where they just want to figure out, just want to push it so that it gets most things right, actually. And those are the three pre-training steps for the image side, actually. Right, so now we've covered this side. Now we've got the other side, the Vision 2 language generative learning, which I also just cover really shortly, actually, in the paper. So now we've got like our image encoder, right? Put in text. We've got our query tokens here. We get our query tokens out. As I already said, we've got the fully connected layer here to shape the tokens in a way that we can put them in to a language model decoder, for example, right? Or large language model decoder. And then, it's also language modeling loss. So we just want to get the best output possible, actually. And we're just training and adapting the query tokens again until we get as good as possible, basically. And they actually have two settings for it. So here it's just a decoder-based model, right? They also say, okay, we can also do it with an encoder-decoder model. And for this, they are actually using this, what they call it, prefix language model loss or something. So they actually connect these query tokens with like part of the output they want, like the first part of the output, and then put that into the encoder, then that goes to the decoder, right? And the decoder then is tasked to output like the continuation of the sentence. And that's basically the whole second part. There's not that much to it, I would say. But I also have to admit I'm more of a computer vision guy, so I'm not that deep into, okay, how can I train the large language models, or how do I do all that stuff? So probably there are more details that can be said about it. But as I said in the paper, they're really short about it. And from my side, it's also like, okay, it's pretty straightforward, actually, this part of the training. So let's have a look at the data they're actually using. Right, so they're using these 6 data sets, and the interesting part is it's exactly the same data they already used for the first BLIP paper. It's a COCO dataset, a visual genome dataset, CC3M, CC12M, SBU, and Lion 400M, right? Where they just use 150 million from these 400 million samples. But in total, they're using 129 million samples, and well, there's 150 million from Leon 400M, so it's like the majority from here. And actually, every dataset that has this asterisk is a web dataset, so that means it's scraped from the web. And the problem with web datasets can be that they are quite noisy, right? So in general, all the datasets are like image language pairs. So mostly it's like here, you can see it's an image, right? And there's, for example, the web description is from bridge near my house, right? Because somebody, I don't know, put it on a blog or something and then just wrote the caption from bridge near my house. Of course, for training, that's not really good. So what they're doing is they're also creating synthetic captions using the BLIP model, actually, BLIP-L. And then, for example, they get a flock of birds flying over a lake at sunset. And they're actually creating not just one caption, but 10 synthetic captions. And then they keep the best two of them. So what means the best? Right, they're to find the best ones, they're actually using the text image similarity from this clip model here. And then, yeah, they try to figure out, okay, maybe sometimes the web caption actually is the best, but sometimes it's also synthetic is better. And then they actually keep two captions for each image, which also is interesting. So they're not saying, okay, we just want to find one best, but we keep two. And then they just sample randomly at every run, basically, which of these two captions they're using. Um, I think they're not going into detail what exactly is like the advantage of it, or if it is any advantage. But yeah, surely is an interesting approach to keep two of them. Okay. Yeah, and for training architectures, so they're experimenting with two vision encoders, basically. One of the vision transformer large with 14 patch size and a bigger vision transformer. I'm always not sure what the G stands for, if it's giant or I don't know, giga, something like that. So a smaller one and a bigger one, even though large already is large, right? But yeah. And on the other side of the large language models, they are using the OPT family, stuff by Meta, right? And the FLAN T5 family, where OPT is an encoder-based large language, decoder-based large language model, and the FLAN T5 is encoder-decoder large language models. Okay, so now for the training settings, actually, right? So that's like the nerdy stuff that interests the data scientists, machine learning engineers. Yeah, so they are training for 250K steps in the first run, so the image representation learning, and then 80K steps in the Vision 2 language generative learning. And yeah, they're using floating point 16 precision, and for the T5 family, B float 16. They're training for 6 days in the first part, and then 3 days in the second part. And they're using a cluster of 16 A140 gigabyte GPUs, which actually is not that many, right? So seeing the time and the resources they used here, that's actually one of the things they also always say, okay, the main advantage of our approach is that it's just really feasible to train, right? So it's not extremely costly. I mean, 16800 is nothing you have at home, but it's still not like on the size of some stuff that Google trains or something, or Meta. So yeah, it's still quite feasible to train, actually. Yeah, and then of course they have like the experiment results, right? So here they've got it on the visual question answering with zero shot stuff. So basically they have not fine-tuned anything. It's just after the pre-training they validated. And one thing you can see here is that when the model sizes actually get bigger, the performance gets better, which is something that you might expect. Yeah. then yeah, it really is like that. That's what these tables can say, and then they say, okay, they can outperform like bigger models, way bigger models actually, um, and a lot of these tasks. And they also, yeah, experiment here. I think that's with the fine-tuned. Is that the fine-tuned one, or is that the fine-tuned? No, I think that's the fine-tuned one, where they, yeah, actually fine-tune the query transformer and the image encoder. So they just leave the large language model frozen. But for fine-tuning, yeah, they basically unfreeze the image encoder and then also, yeah, take the image encoder's weights and adapt them for the fine-tuning. And again, you can see, okay, bigger is better, and they are pretty good in performance. Else they probably wouldn't put it in here. And they're also doing experiments with captioning, right? So they, yeah, the three main tasks they're doing really is visual question answering, like chatting what's in the image, and captioning. It's really just like, okay, what is in the image? And here you can see, they're also pretty good. They've got like best scores down here, especially for this no caps set. And for the captioning, it's similar to the visual question answering, that they update the Q former and image encoder weights and leave the large language model frozen. And for the last thing they experimented with, that's retrieval. So it's image to text or text to image retrieval. That means when you have like a pool of images, right? And then you've got a text, then you say, okay, give me the image that is most similar to this text. That's a text to image retrieval. And when you have a pool of texts and one image, and you want to get the text that is most similar to your image, then that's image to text retrieval. And actually for this task, they don't need the large language model, so they just completely leave that out and only fine tune the image encoder and the query transformer. No, Q former, it's not query, Q former. That's the right term for it. Yeah. And as well here, right, the performance is outstanding. There's even some 100s in there. They're doing pretty well. So all in all, it is a pretty good model. And yeah, right now it's maybe the best model you can use for yeah, chatting with image about images. I don't know how far GPT-4 image stuff is right now, but yeah, I guess when that comes out, it will be pretty impressive as well. Probably better than BLIP-2, um, but especially for open source things, BLIP-2 is pretty nice because you can also, yeah, I mean, you can plug in different image encoders, different large language models. It's quite modular in the whole setup. Um, so yeah, I like the paper in general. Um, Maybe my main criticism, like regarding to the paper, is that they could have been a bit more descriptive about the losses they're using. So mostly the losses are similar to what they used in the first BLIP paper, and I think that's why they don't go into detail on much of that, because they're just like, oh yeah, it's in the first paper, so we're not talking about it, but they could use a little more detail. So not everyone has to go back to the first paper and look at what it is about actually. Yeah, so that's, I guess, my main criticism about this whole thing. Okay, so for this presentation part, this is the end. Thank you for now. We will go on and look at how you can actually use it with the transformers library from Hugging Face, just for like 5 minutes or so. But if you have questions about the paper right now, this might be a good time to ask. No? Okay, great. Then I was either really confusing or really good at explaining stuff. So first of all, there's a great space you can use, right? It's the one by Hysts actually. There's an official by Salesforce, but the one by Salesforce is not GPU powered, and then you have to wait an eternity. So I recommend this one by Hysts, who's actually part of the Hugging Face stuff as well. So that will keep on running. And yeah, here you can basically try out, right, the chatting, for example, or the captioning. You can caption here, like caption it. And yeah, you get a house that looks like it's upside down. And then here, over here, you can chat. So here you've got like your text box. You can just chat with it. How could someone get out of the house? A ramp on the side of the house. Well, it's a slide, but it's okay. And then you can go on chatting, right? Or you can ask, isn't it a slide? Wait a second. No, it is a house. True, it is a house. Yeah, it's quite funny. So it's I had a lot of funny conversations with it already, um, similar to this actually. So you always feel like, okay, I should have explained it a bit better. Um, it's not that good at getting these contexts from before, like, but yeah. So make sure to be really uh, expressive about what you want here. But yeah, let's quickly have a look at how you can actually use that stuff right in code. So there's this great notebook by Niels. He's also one from of the Hugging Face stuff, and he's got this transformer tutorials GitHub repository where he has just a bunch of notebooks for all kinds of models that are in transformers. There's really a lot of them right now. And of course, there's also one for BLIP-2. So here you really just go through, okay, set up everything. In this version, it's even, I think it's, um, optimized a bit with bits and bytes to run on int8 precision. So yeah, you load images, right? Blah blah blah. Okay, that's like the basic image stuff. And then you get to the transformers part. You can use the auto processor class actually to use the weights. Um, so here he loads the OPT 2.7 billion model, and then you can load the BLIP-2 class from transformers. This one for conditional generation. You can also say from pre-trained again, right? So again, this model says force, blah blah blah. Yeah, then you do the torch, CUDA, blah blah, the usual stuff, Um, and then you can start by passing the image you loaded up there to the processor, which gives you inputs, and then you can generate IDs by loading the model and call generate with the inputs, and then you get a generated text processor batch decode, right? And then you can print the text. So that's if you just want captioning, you just have to put in an image, of course, right? And if you actually, that's prompted image captioning. So that's if you want to use a prompt and then get like an image caption again. But sometimes this helps to get a better image caption actually when you do this, like this is a picture of, and then you can get better results than just saying, okay, here's just the image. But in this case, I think it doesn't matter actually. And yeah, it's actually the same process as above, that just that you also have this prompt which you can put into the processor. So it's really just this one parameter here where we say, okay, in the processor, we've got a text and that's the prompt. And then you can just call it again, generate with a model and then decode it again with the processor and you get the text actually. So what if you want to chat with it, right? So here's a visual question answering. Again, the same, but then if you want like continuous stuff, here you can just actually concatenate basically the prompts, right? So you've got this template, question and answer, and then you just get the question you ask, put it into the question one, then you get back the answer, you put it into the answer brackets, and then for the next one, you basically put that in at the start of the prompt and just add the next stuff you want to ask, right? So in the end, you just put a lot of these question answer things in a big array if you want, and that's how you can then prompt it, yeah, to chat with you basically. So I think it's pretty straightforward. That's the nice thing about Transformers library. You don't need many lines of code. And yeah, I guess you can have a look yourself if you want. I will also put these into like the last slide, put some links into the last slide when I upload them, so then you can check it out yourself. Okay, now that is it from my side. Okay, maybe for you, Chet Kensington, the question, the query tokens, um, are they only learned with the cross attention, you say? Now, well, the way they are learned is right through all these things here, through these losses, basically, right? So you then adapt them. You get your loss from image text matching, from image text contrastive learning, whatever. You get your big loss, and then you adapt them somehow, and they get information from the image encoder through the cross attention, but they also get information from the text tokens through the self attention layer, basically. Are the values all the same for all images? Yeah, in a way they are. Yeah. So once you've learned, like when you have learned the whole stuff, these query tokens have those some values that are set. And then when you do an inference, of course, then this image encoder again has a cross attention and yeah, will change the token values according to like what the image is like. But the initial value is the same for all images. Yeah. Okay, great. Well then, if there are no more questions, have a great day, evening, morning, wherever you are. I don't know. And maybe see you the next time.